My work focuses on computer vision, video understanding, machine learning, robotics, and I work on sort of many aspects of problems there. But one of particular interest in terms of, say, societal relevance is the issue of manipulating videos. Right, so videos are our common communication medium of the 21st century. YouTube gets 300 hours of video uploaded every minute. Right? In this hour of talking, there will be 3,600 times 300 hours of video uploaded to YouTube. That's a significant amount of video uploaded to YouTube. Videos cross cultural barriers. They cross markets. They flatten the economy. And for the most part, we think of video as valuable. But we can do things to video that might not be so good. When you think of interstate relations, for example. Right? So this is a talk about video segmentation and video object removal. And maybe you can call it video inpainting. All right, so here you see upper left, this is the raw input video. Upper right is a segmentation of an object in the video. I believe this is actually a human-drawn ground truth segmentation. So computer vision is good, but maybe not that good yet. Bottom left is an automatic output with that segmentation sort of overlaid on the video. And bottom right is the same video without that object in it, automatically removed. So we've seen, in Hollywood, right, this is done pretty well by artists, by humans, who spend a significant amount of time doing a process called rotoscoping. So they draw the boundary and laboriously, frame to frame. They'll even set alpha matting levels. It's ridiculously laborious. What we're trying to do is make this easier. Okay, there are two parts to this. One is video object segmentation. One is object removal / inpainting. And again, I'll just focus on some video object segmentation just to make it's only 12 minutes to talk here, so I'm talking about one thing, right? So let's talk about object segmentation or video segmentation, right? So back when I began as a grad student 15 years ago, we thought of video as a graph, right? So we have some pixels. They relate. They're related in space and they're related in time. And usually we would maybe connect them, 6 neighbor connectivity over these pixels. And we'd write down some objective function that talked about what we thought were the good, maybe the visual gestalt, the properties of the regions in the video that we'd like to group together versus keep apart. So if they have similar color distributions or similar texture, then we want to group them together so that we can ultimately color the graph, right? So these are arbitrary colors that just mean yellow is all one group and red is all another group and blue is all another group. And usually this was either the result of a handwritten algorithm or the solution to an objective function. I prefer the latter, but many fast algorithms exist for the former. And you go and do this repeatedly so that you can build a hierarchical graph that captures the phenomena at multiple scales. So you ultimately get a graph or a hierarchy over plausible segmentations of the video that becomes your new representation. You'd like to then use this type of a output to do further processing, right? So a fine level close to the pixels, bottom left here, and then top right is a coarse level. But as you'll see, nowhere in this hierarchy is one object like the bicyclist or the helmet or the upper body. Right? Because this bottom-up segmentation can't really get the semantic output, the semantic value that you'd expect to find. So we spend a lot of time on, say, semantic segmentation. One plausible approach to that is to take that hierarchy and try to flatten the hierarchy by guiding it with a post hoc feature. For example, motion entropy, or humanness, or carness. As machine learning invaded computer vision, there is this move from low-level features to, say, mid or high-level features like carness or humanness. What you see here is a 7-layer hierarchy in which we are rendering a notion of entropy, a discretized distribution over entropy, where I think we have maybe 8 angular directions and maybe 6 magnitudes. And this is the MATLAB jet color space. So red means lots of entropy over that distribution of optical flow in these segments, and blue means low. The intuition here is that we would like to come up with a flattened version, a selection across the hierarchy that would balance the amount of entropy across the segments. Right? So when we have a large background segment, not much is happening, fine, we can keep it as a large segment. But when we have a foreground segment, a lot is happening, we'd want to make it a finer segmentation. So we optimize this function and get a flattened hierarchy based on some sort of post hoc guidance. Okay, so here's some outputs that you see from that, right? So input is a bottom-up segmentation hierarchy guided by either this humanness or the carness entropy, which just basically means we have a classifier that can measure humanness or carness in a window, and we run that over the entire over the entire frame and get a notion of entropy over that distribution. And then we have a measure of what is being selected at different layers of the hierarchy. So red in this column here means higher in the hierarchy, and blue means lower in the hierarchy. And we can flatten it. We can do that for humans or from cars. We get reasonable outputs, right? So when we care about cars, we start to see a flattened hierarchy that is actually finding the car that's in the background. And when we care about humans, we see a fine hierarchy that's caring about humans and not so much the cars and so on. But we're still not there. We can't get to the point that it was a sort of video object segmentation that we could use to remove that object, say a human or a car. So enter 2012, 2014, the world of deep learning. So how has that impacted how we saw video object segmentation? Significantly. So here's a standard way of doing sort of video object segmentation now. Right? So you take a base network, like a ResNet or a DGD network that's trained on a lot of photos. Okay? You can apply that to basically pull out specific content in video frames. It's not going to get you too far, but at least it's a good feature space in which to work on. Right? So train on a good amount of features. Then take a second training process called a parent network here. Right? So take that base network, fine-tune it for the problem of video object segmentation by training it on actual segmentations. Right, so humans went through and drew those boundaries, these white boundaries here drawn by humans, and it teaches the network how to prefer a single video object segmentation on a video from the background. Finally, at actual inference time, you have a human available. That human is going to give you one frame. Because in most videos, there are many possible objects that we can care about. So the human just gives you one frame of segmentation. I care about that person. Or I care about the rider of the motorcycle, not the motorcycle. They're going to give you one frame segmentation. And so this is a question of how can we best use the output of that human to do a segmentation, right? To do that fine-tuned segmentation. Okay, this is sort of a state-of-the-art method. And so what my group has been focusing on is this observation that says it matters what frame you ask the human for. Right? So the typical thing in the vision community so far has been just ask for the first frame. It's the natural thing to do. You show them the first frame, they segment it, and then they apply that to learn how to segment the rest of the video. It makes sense. But it's not the best thing to do. In fact, it's rather far from the best thing to do. So what you see here is the horizontal axis is the frame index that was segmented, and the vertical axis is a measure of performance when that training was applied to all of the video. So the first frame here gets something like 55% or 45%. The best frame, these are not percentages, sorry, so .45 and the best frame is something like .12. That's more than double, almost triple the performance. And it's obvious that we could then train a model to suggest what are the useful frames to annotate. Right? Each row is a video here. Clearly, in the first row here, this is a bad frame, this is a worse frame, this is a decent frame, these are okay frames, right? So we want to do that. Okay, so what we've been working on now is a model called bubble nets. Right? So everyone's taking computer science 101 in this room probably. Right? So this is how to train a deep network to do bubble sorting for you on the fly. Right? So assume we have 10 frames of the video, rather than directly trying to predict the performance of that frame for this problem. There's not enough training data for that. Right? So instead, we're going to predict the relative performance. So take m random frames, say 10, then take pairs of frames and see which pair performs better when trained, which of those two performs better when trained and applied to those m frames. We have a ridiculous amount of data then for that type of problem. Okay, and at runtime, do this comparison on the fly for your input video and basically bubble sort one of the frames all the way up to the top as the best frame to use. That's the basic idea. Okay, this is the network diagram. Any interest? I don't know. I see a lot of talks with deep network diagrams, and then I find it hard to understand them when I see them. So it's okay. That's what we do. Okay, this is that model applied to those. That intuition applied to real data. Okay, so again, if we were to use the first frame, this overall, this is like a dice metric of accuracy. We get something like 1.2. Choose the bubble sorted frame. Now it's not perfect. Like the actual perfect frame would have been one of this one here or this one, but it's certainly doing a better job than the top, which was the first frame performance there. Okay, when applied to this as well, we see it's doing as good a job on this example. I'd like to tell you that these are cherry-picked examples, but these are not. These are just arbitrary examples that what my colleague Red Griffin just pulled out of the data set for. Actually, numerically, if you're able to do deep bubble sort, we are within 0.15 to the upper bound of performance, whereas if we choose the first one, we are another 15.15 away from it. Right? So this is a good idea. Right? So, okay, so in all of the results I showed you in the first video, we're done with this method here. So when you are able to get good video object segmentation, we're able to successfully manipulate videos, and the implications to society, I think, are well beyond entertainment. Okay. Furthermore, my lab has a policy of releasing all code and data open source, so you can find the stuff we talked about on the website. And finally, I have to plug the fact that my company, Voxel 51, is hiring 8 of you soon, or 8 people like you pretty soon. So we'd love to talk to you. We'll have a poster, and I'll also be on the entrepreneur panel later this evening. So thanks for your attention. I'm happy to take questions.